in a rapid way. Schema 10. Okay, here we go. Pullbacks and pushouts. So once again, we're going to use our favorite schema, our schema graph. But again, this has nothing to do with graphs in particular. It's just, okay, I've got to restart the kernel because apparently I was running this before. Sorry. Let me restart the kernel so I don't diverge from what you see. Okay, so I'm going to import Catlab. I'm going to show schema. I'm going to be operating in the C set schema for graphs. So C here is graphs, but again, it's nothing to do with it being built in. It just we could do this for any category C. I'm going to create a single vertex. I'm going to create a bunch of graphs again. A single vertex, a connected pair, and I again apologize for using this old syntax. AC set colim is much nicer. We saw before I could take homomorphisms. And here, this is going to be important because pushouts and pullbacks are going to operate in terms of homomorphisms. Like we have to specify homomorphisms using Arthur. Yeah.
Have you tried running this, rerunning it from what could be my version?
And where? Yes, I have.
It says GU. Undefined variable in cell 36.
Okay. Oh, line 36? Cell 36. Okay, yeah. So this is some material we weren't going to be covering, but it is possible down there.
No, must be a version.
Okay. There is something called GUnit above, and one thing you want to do is do it. Oh, okay. GUnit I did cut out. It's a yeah. So I can tell you. Sorry.
Did you rerun it?
I ran all that we're going to be getting to, which goes down to doesn't go down that far. I reran it down to line 26. I rerun it down to line 26. The rest is for students exploring more deeply, so I didn't rerun all of that. But I will get you a fix for that. Sorry?
Just restart the kernel and run the whole notebook.
Okay. Oh, I see. Okay. Yeah, that makes sense. I'll send you. Thank you for flagging that. I did do some cleanup, which might have affected that code down there, but I did run it all the way down that we're going to be presenting. So apologies. Yeah.
Notebook 2 also had an error, but I just assumed it was a version thing. I never completely reran it. But the other
Really? Okay.
Fine.
Okay. Yeah. So maybe you could show that to me afterwards or show it to Shayan. That'll be great. Okay. Yeah. So I cut out some material from these that I thought was a duplicate, and it may be that I cut something out related to that. That is in an area of it that as I say, I didn't rerun because I wasn't planning to cover it in class here. Okay. So what we're going to do here is we're going to be taking pushouts. Now, pushouts are like, you may remember coproduct was like putting two graphs next to each other. We had this graph next to that one. It's kind of like putting, as my colleague John By says, two graphs next, two tinker toy pieces next to each other. So maybe we have a reciprocal graph and we have, one single edge graph. Just putting them next to each other like two solid cubes. That's coproduct. It's like graph A, graph B, and this would be expressed as A plus B. We're going to be talking now about something that's a variant in this, but it's much more powerful, much more useful and for a lot of our needs, which is something called a pushout. And a pushout is going to be like a coproduct, but we're going to have equivalence classes. We're gonna take as equivalent. We're gonna identify certain features of graph A with certain features of graph B. Treat them as the same. And this can result in things like here. Here's our reciprocal graph, where we have the second one glued to graph A. So when Xiaoyan was saying colim before, Colon is a push is reduces to a push out when it's between two things. So we're going to be defining this. And I'd like to show you the square we're going to be dealing with. It's going to be this one here. So excuse me, we're dealing now with this resolution issue. So I am going to have to get this moved from here. Gosh, apologies. This is horizontally.
The left-hand side.
Yeah, I actually
Like, I'm using Jupyter Labs.
Yeah. The problem is maybe you'll excuse me for just a second. What I'm going to do is stop screen sharing. I'm going to switch to the correct resolution, and I'll switch back. Okay, now we're all set. We should be able to see the full screen. I just I didn't have the forethought to adjust the resolution when I plugged it into my computer the second time. So here we go. Oops. Sorry. Here we go. So we're going to be taking the push out of two graphs. Now, the push out is like a co-product. So we're going to take a graph that's this one here. That's shown on the board. That's our graph B, and our graph A. That's this one here. It's a reciprocal pair. And we're going to combine them, but we're going to combine them in a way that glues them around anything mapped to, it glues together a point, something in A and something in B that are mapped to from the same thing in graph C. So graph C here is going to be a graph, and its vertices will map to vertices in A, its vertices will map to vertices in B. And if a given thing in C, a given vertex in C maps to a specific vertex in A, call it, V sub A, and it maps to a certain vertex in B called V sub B, then we will identify those two vertices in A and B when we glue them together. So you can see what happens. We are putting this graph and this graph next to each other for the most part, but we are considering this vertex and this vertex to be the same vertex. So they are glued together. They are affixed by that vertex. Why that vertex is considered the same? Because it's mapped from the same vertex in C. We will see this can apply for edges as well. So here we are putting A and B next to each other, but glued together around C, identifying things in A and B that are mapped to from the same C, considering them in the same equivalence class. So let's see that. How do we do that? Well, we have to do it in terms of the homomorphisms. We have to specify this homomorphism, this homomorphism here, how C, a certain graph C, which is the single vertex, maps into our reciprocal pair. That's this one down here. That's a graph. We have two choices for how that can map into that. Those are the homomorphisms. We will do it in terms of how this graph can map into this graph. How many choices do we have here? Well, oops, not O homomorphisms. Should be homomorphisms. There's two choices there. And we're going to specify one of those. We're going to specify the map here to here, which maps it to this proximal edge. We're going to map it here to here, the map to that, the proximal vertex. We're going to map it here to here, the maps to that proximal vertex. So we picked out one of those homomorphisms here, the first one, and we picked out the first of these ones. I'm specifying here S, that's this homomorphism from single vertex to reciprocal pair, and T, that's the homomorphism from the single vertex to the connected pair. Having done that, we can say, take the push out of these and show it to me. Show me the result. And it is computing it, and there's our result. And I apologize, I can now afford the luxuries of a larger screen. So we've put together these two graphs, this graph here and this graph here into the same graph, identifying certain features. The features mapped to by the same structures here. So we had these graphs, we defined them. These are just C-sets as far as Catlab is concerned. It's nothing about them being graphs that allows it to do this. It's just their C-sets, and any C-sets we can take pushouts. By doing something similar, specify the homomorphisms. Now we're going to do something a little bit more textured. We're going to take a pushout, but instead of taking a pushout around a single vertex, identifying a single vertex, we're going to do it around an edge. So C is still going to be a graph. It was a graph before, so just a particularly degenerate graph, just a vertex. Now it's going to be a whole edge with two vertices on either side. Those are the natural building blocks. And we're going to have one of the items is taken the pushout being our, you may remember this row called graph A from earlier. And then graph B is going to be these two end-to-end ones. And we're going to take their pushout around C. So again, anything that's mapped to by the same structure in C, by this edge, is going to be identified in A and B. So this will be identified with that. The things in red will be identified with the things in red. So this one and this one will be considered the same when we put these two next to each other. So we put these two next to each other, but we consider the red areas the same. This is what we get out. This has the structure of this in it. That's why there's a homomorphism here. This has the structure of this in it. There you go. That's why there's a homomorphism here. But these components are identified. That's why it's a pushout around C, not a coproduct around C. If we had just asked for a coproduct around C, well, we would have gotten this and this just right next to each other. Next to each other, like Tinker Toy pieces that are disconnected. This just sitting next to that. But a pushout, a co-limit, is like a coproduct. It's like having both, but putting some in the same equivalence class, identifying the structure. And that's what we've done. This can be done, because we're not topos, it can be done for any sets. If we're happen to do it for graphs, it'd be done with reflexive graphs, symmetric graphs, stock and flow diagrams, causal loop diagrams, Petri nets, so on and so on. Yeah. Yes.
But rather than with every individual pushout that we wish to create, defining these equations as you showed us before.
Yep.
Is there a way to kind of encode this as an object within the language, and then I can say TQ is SP? And suddenly I start to get all of these out as special.
I see what you're saying. You're saying, so if I understand, is it Gerard?
Sure.
Gerald. Sorry. I think I see what you're saying. You're saying, look, could we treat the whole pullback square as, or excuse me, pushout square here as itself a construct?
Right.
And could it be something we reify as a thing? And in fact, it is. In fact, behind the scenes, I'm just hiding it. And if I could have the temerity to sort of show, depart from the beaten track here, I will add a cell here, and I will say, instead of asking about the apex of it, I will say, hey, give me, oops, I need a, GA, sorry. What am I doing? Did I not execute GA here? Okay, sorry, here we go. I might not have executed that earlier, and apologies. So here, okay, yeah. So this is exactly what we have. So here's our pushout. This is our whole structure, our AC set color. It actually has the whole structure of this. If we ask for its sorry. If we asked for its apex, now we're talking about this particular sub piece of it, which is just a component of that. Here's our apex of it.
Apex means lower right corner of
it's the apex in the sense that all the arrows are here that are coming into it, and so it's at like the top of it, as it were, in the terms of this directionality. We could ask for its other parts if we wanted to extract them. Here we're asking about this apex. Now, this apex is itself, if you note, when I ask about that, it is itself a CSAT. It's a graph in this case, because we happen to be working with schema category graphs. That is itself a graph, and we could visualize it, and we would see that. Okay. I don't think I will go through all of the details here, but I will say that we can do the same thing with pullbacks, and pullbacks are like pushouts are more sort of flexible and more fine-grained way of thinking about co-products, or version of co-products. Pullbacks will build on the idea of a product of two graphs, but here we're not going to be just taking a product. We'll be taking a product in a way that demands a certain compatibility between A and B. If, as Eugenia Chang says, a product, if you have a bunch of pants and a bunch of shirts, a product would be like taking all of the set of pants and considering all pairs of pants and shirts. We might take a pullback, which would be like taking shirts and pants of the same color. They're pairs of A and B's, just like with product, but they're pairs of A and B that are in some sense compatible. They have the same color, for example. But the generalization of this is via a push-out square, or pullback square rather, where we have, instead of the push-out square, we're going to have a pullback square. And the idea with a pullback square is we're going to have here A, might be our graph, B might be another graph, and we're going to have an object C here. This could be some sort of type graph, and we're going to have a product of A and B over C, or we say fibered by C, meaning that if we consider this and we project down to A, and this is like pairs of A and B that map to the same C. So here's is going to be the product of B. But the pairs of A and B that map down to the same C. So this might be colors for our case. This might be pants, this might be shirts, and they map down to the same color. Or we have graphs, two graphs that map to the same structure in the type graph represented by C.
So
yeah. Mm-hmm.
Good example, take it in relation to join.
That's right. Exactly. That's precise. In a database. Yeah. We're taking the join, we're taking contents of table A of the database with table B of the database joined over the customer ID. Yeah. Or joined over the employee ID, or joined over the department, or what have you. That is very true to this deep connection between CSATs and databases. The categorical perspective on databases is one that's been now well explored in the literature, in which is very much represented in Catlab. One of the uses of database of CSATs and Catlab is to do functorial data migration from one schema to another. Declarative. I'm not going to go into these, but I will say that the notion of a pullback of two structures is like a constrained product where we need the things, the pairs in the product to have some common feature, like you would have in a joint for figures. Okay. I will simply mention, I'm not going to go into it. We're living, I so appreciate your patience with this.